Let's begin with the principle of virtual work. So before we talk about principle of virtual work, I recommend you to watch my previous video on virtual displacement because it is very essential to understand virtual displacement before you understand virtual work. Now let's come back to this. Okay, suppose we have a mechanical system where there are many particles. Now, how we write the force on the ith particle of the system? We say it is Fi bar, right? So Fi bar is the force on the ith particle of a system. Now we consider a system in equilibrium. Okay, we call specifically that as translational equilibrium. So what does the equilibrium mean? Equilibrium means the force on each particle is zero. So Fi bar is equal to zero. So there are systems like that. For example, here you can see, suppose there is a ground and on that ground a block is placed simply. Now you can see the upward normal reaction is equal to the downwards mg force. So the net force is zero on this particular block, right? So if I place another block on the top of it, another block on top of it, it is still in equilibrium because on all the forces on the blocks are zero. If I consider this system and move it with a constant velocity, let's say the surface is the floor of a bus or a car, and if I move that car with a constant velocity, then still these are in equilibrium because the net force is zero, right? So Fi bar is equal to 0 bar is the system where you are in equilibrium, right? Now, what we are going to do here is that we are going to define something like this: Fi bar dot delta Ri bar, right? So, what is Fi bar dot delta Ri bar? It is an infinitesimal work, right? Infinitesimal work with not the real displacement but the virtual displacement. So you can say this is a virtual work, right? It is a virtual work. So if I take the summation of this over I, Fi bar dot delta Ri bar, right? So this is delta Wi. So here Fi bar dot delta Ri bar summation over I is nothing but equal to 0. Why? Because each Fi bar is 0, as I have said, for such system. So for the systems in equilibrium, we can say this is true, right? And this is Fi bar, and Fi bar can be decomposed further like this: Fi bar A, that is the applied force plus the force of constraint on the ith particle. This is the force applied on the ith particle. This is the force of constraint on the ith particle. Now, what I'm going to do is I'm going to substitute this Fi bar in this equation. So what we will get is this summation over I, Fi bar A plus small Fi bar dot delta Ri bar. But since this is equal to 0, I am going to write it as equal to 0. And here you will get summation over I, Fi bar A dot del Ri bar plus summation over I, Fi bar dot del Ri bar. This is going to be 0, right? So now this is the principle. Now here, if I see this term is nothing but the constraint virtual work done by the constraint forces, right? Now we have seen in our previous video that most of the times, not previous video, but before, we have seen mechanical systems where the constraint forces do not do any work. For example, if a block is sliding on a wedge, right, like this, the constraint force is perpendicular to the displacement always. So of course the dot product is going to be 0. In a pulley system also, or Atwood machine, you can see, you have seen the work done by the tension forces is 0. So most of the mechanical systems are such that the constraint forces work done will become 0 for a real displacement. But when the surfaces are themselves are in motion, like the previous video's case, where you had a wedge which was moving with a certain velocity v0 towards right direction, in that case, the work done by the work done by the constraint forces did not go to 0 because of the component of dt, right? It depends explicitly on time. So now we, in this case also, we can make our virtual work 0 because the virtual displacement does not depend on dt, right? So here dt will be 0, and then you can say fi bar dot delta ri bar equal to 0. Safely you can say that. So then you can see summation over I fi bar a dot delta ri bar. So here mostly we are talking about holonomic constraints, right? So non-holonomic constraints are the constraints which are written in the form of inequality, right? But most of the systems that we will deal with are the this much simpler systems where you can safely use this, right? Okay. So now fi bar a dot delta ri bar is equal to 0. Now, this is called the principle of virtual work, right? This is called as the principle of virtual work. This is called as principle of virtual work, right? Now, if you note that this coefficients of delta Ri bar, we cannot set equal to 0. That means this Fi bar A cannot be set equal to 0 because these particular terms are will be independent, no, will not be independent of each other, right? They will be dependent on each other through the equations of constraints. They will be connected by the constraints. So you cannot set them individually to be 0. Now the thing is, what we are going to do is we are going to transform these in such a way that uh, you can do these coefficients of, instead of ri bar there will be delta q. See the coefficients of delta q individually to be 0, and then obtain the equations of motion of the system. You may not understand what I said just now, but you will understand in the future videos. Thank you.